All right. So we will continue yesterday's problem. And today's class I am taking as a substitute of next Thursday's class. So next Thursday I will not be able to take the class. I have an important meeting which is unavoidable. I have to attend that. So, and today we will try to also finish the syllabus for the midterm exam so that you have sufficient time for preparation. Can you see the screen?
Yes, sir.
Okay, good. So
Yes, sir.
yes, we were discussing about a problem on real cycle yesterday. So what was the problem? So the problem was given as real cycle with not reheating, sorry, a two spool industrial gas turbine was present. Two spool means there are two shafts. So one shaft runs the compressor and the high pressure turbine assembly, and the second shaft runs the second turbine. Okay, it passes through the outer shaft basically. They are like concentric cylinders, and so in between the compressor turbine, obviously there is the combustion chamber, then high pressure turbine, and then the low pressure turbine. So the low pressure turbine, the entire work is used for running the generators, basically for generating power. And the entire work output of the high pressure turbine is used for just running the compressor. Okay. And because it was a real cycle, we assume certain efficiencies of the different devices. For example, the compressor efficiency was 87%, isentropic efficiency because nothing is mentioned here. For both the turbines, we had taken 89% efficiency. And for the combustion process, our combustion efficiency is 99%. All these are realistic values. Okay, like all these are values from practical cases. It's raining very heavily here. And ambient conditions are so because it's a ground-based turbine, industrial turbines. Ambient conditions are atmospheric pressure at the sea level 101.3 kPa and 15 degrees centigrade, so 288 Kelvin. Compressor pressure ratio is 9, and nothing is mentioned about the pressure losses. So we will assume that there are no pressure losses. And if there are pressure losses, you should be able to take that into account. I have uploaded a few problems, actually different versions of the same problem, so that you can compare different cases. What is the effect of regenerator? What is the effect of reheat? What is the effect of intercooling? For real cycles, you should. I have posted it as an assignment, but you don't have to submit it. You can just first try to solve them on your own, and then take a look at the. Then you can take a look at the solutions that are provided. 4 problems are there, so you can expect similar type of problems in this course, like in the exams. So you can just try to solve the problem without seeing the solution first, and then you can take a look at the solution. So in these cases, we have also considered pressure losses. For example, then in regenerator pressure losses, combustion chamber pressure losses, everything is there. So let us come back to today's problem, which we have discussed, we just started yesterday. And the delivery pressure of the turbine was also given. If it is not given, we will assume that it is atmospheric pressure. Because it is given and it is different from atmospheric pressure, so we have to separately account for that in our calculation. Okay, so this diagram was wrong as we have discussed. P05 should be greater than P01. We needed to calculate the fuel air ratio, the net specific power, the efficiency of the cycle, and the specific fuel consumption, which we have defined yesterday. Fuel consumption per unit power, right? So let me just again run through the problem quickly once, what we had done, discussed yesterday, and then we will continue. So we started from the atmospheric conditions. So I will keep this open, this diagram. We started from the atmospheric conditions, PA and TA, and at the inlet, because there is almost negligible velocity. Obviously, there is some velocity, otherwise how the air will enter. But that we are going to neglect in this case because it is very small. So P01 is equal to PA plus VA square by T01 is equal to TA plus VA square by 2Cp by definition of stagnation temperature. So because VA we are neglecting, so T01 is equal to TA, 288 Kelvin. Okay. And similarly, P01 is equal to PA, 101.3 kilopascal. And pressure ratio is given for the compressor as 9. So T02S by T01, we had first calculated to find the point T02S because it is required to find the point T02. So we calculated this as RC to the power gamma minus 1 by gamma for air. Okay. So for air, we can take gamma as 1.4. We have discussed previously. So this came out to be 1.8734. And from this, we found T02S to be 539.5519 Kelvin. Okay. And using the definition of efficiency of compressor, isentropic efficiency of compressor, which is equal to T02S minus T01 by T02 minus T01, we found that T02 is 577.14 Kelvin. So you can see that even at the compressor outlet also, relatively the temperature, the actual temperature is quite high, but relative to the other locations, the temperature is actually low. So this temperature air is actually used for cooling the turbine blades. So for this case, so from this point, in this case, it is not considered, but if you need, in actual cases, you will need cooling air for the turbine. So it will go from the compressor outlet, and typical temperature will be somewhere around this 550 Kelvin, something like that. So it is around 300 degrees centigrade. But still, it is sufficient to cool the turbine. So then so 0.02 is now known, 0.0102 is known. 0.03 is also known because Tmax was given as 1380 Kelvin. So that is equal to the temp. So Tmax occurs at the inlet of the high pressure turbine or outlet of the combustion chamber. So therefore T03 equal to 1380 Kelvin. And since no data was given regarding pressure loss, we will assume that there is no pressure loss in the combustion chamber. So P03 is equal to P02. If pressure loss is given, it will be given as, means generally it is some percentage of the compressor outlet pressure, say 4% pressure loss occurs. So in that case, P03 will be 0.96 into P02. Okay. So in this case, it is just hold on for a second. Yes. So in this case, P03 equal to P02, and P02 obviously we can find from P01 using compression ratio or compressor pressure ratio. And we found that this is equal to 911.7 kilopascal. So after that, what we did? So for the combustion chamber, the unknown is the, like we want to find out the fuel air ratio. Okay, because T03 and T02 both are known. So the unknown is actually the fuel air ratio. So using energy balance, we can write that the calorific value of the fuel per kg into mass flow rate of fuel, F. So F is actually the fuel air ratio. So it is the mass flow rate of fuel per kg of air, right? And eta B is the combustion efficiency. This gives us the actual energy that is increased in the combustion chamber. So this is also equal to basically the energy gained by the gases. So this the mass flow rate of gases at the exit is 1 plus F per unit mass flow rate of air, and this multiplied by CPG T03, which is the enthalpy of air at the exit per unit mass, gives us the enthalpy of air, total enthalpy of air at the exit of the combustion chamber. Okay, and at the inlet of the combustion chamber, the enthalpy is mass flow rate, which is 1 into CPA into T02. So using this, we found F to be equal to 0.0245 The fuel air ratio is 0.0245, which we have already discussed. Typically, fuel air ratios are very low. The air fuel ratio you can see from here is that it is something like 40 point something, or like slightly larger than 40. If it was 0.25, it would have been 40. 0.025, it would have been 40. Yeah, slightly larger than 40. So the next task, so up till this point we have discussed. So next task is to find out this 0.04. Okay. So no information is there regarding the 0.04. Neither do we know the pressure at 0.4, nor do we know the temperature at 0.4. Okay. So if the pressure was known, then we would have, what we would have done? If the pressure was known, we would have found the 0.04s. Okay. So the temperature at 0.4s we would have found. How? By using the pressure ratio. Because P03 is known. If P04s was known, we would have easily calculated the temperature here. And then using efficiency of turbine, we would have found the 0.04. But because the pressure is not known, we cannot do that. So what will we do? We all have one extra information, that the work output from this turbine is entirely used for running the compressor. So that is what we are going to, that information we are going to use. So the work output from the turbine is m dot a plus m dot f, total mass flow rate in the turbine, into Cp of gas into T03 minus T04. Okay. So this is equal to m dot a into Cp of air into T02 minus T01. So which is the, just a second. So which is the compressor work input. So we have assumed that the mechanical efficiency is 1, means 100% efficient. If mechanical efficiency is not 1, if it is 0.99 or something like that, we have to divide this left hand side by 0.99, because the actual work output will needed for running the compressor will be more. So that can be found by dividing this by the mechanical efficiency. Transmission efficiency, it is also called as transmission efficiency. Okay, time. So anyway, so now we can find CPA, we already know 1.005 kilojoule per kg. T02 we have calculated 577, and T01 is known 288. Okay, and 1 plus F we have just now we have calculated. Cp of gas we can assume 1.148 kilojoule per kg Kelvin. For all the problems we will do like that, we have discussed previously. T03 is given 1380 Kelvin, and T04 is the unknown. So based on this, if you calculate, you will find that T04 is 1132.699. We could have done the calculation in the class, but there is no point because it's just a simple calculation. To save time, we not do it. Okay. So if you just calculate using calculator, you find that it is 1132.699 Kelvin. So once we know the temperature, can we proceed to the next point, 0.5, or do we need to find the pressure here? Because temperature is known already. Can we proceed to the next point, or do we need to find the pressure here? P04, is it needed or not?
The pressure at 04 is already given, right?
How is it given? It is
So
not
the
given.
pressure to the inlet of the free turbine is given.
No, it is not at the inlet of the free turbine.
So delivery pressure of free turbine.
Delivery means delivery at the delivery means at the outlet of the free turbine. Okay. The
Okay,
pressure
sir.
that is delivered from the free turbine. Okay. So the outlet pressure is given. That is what I am telling you, that the outlet pressure is not equal to atmospheric pressure. We have drawn wrongly here. Outlet pressure is greater than atmospheric pressure. It is given as 120 kP. So my question is, do we need the pressure at P04? Because enthalpy calculations we just do based on temperature. To find out the efficiency, what do we need to find out? What will be the efficiency in this case? For this realistic turbine, gas turbine. Can somebody please reply? What will be the efficiency? How will you find basically? Means I'm not looking for the exact formula. Nikhilesh,
Yes, sir.
how will you find the efficiency?
So the net work output.
Net work output, that is what I'm asking. Means net work output is what here?
So the net work output is just the free turbine.
Yes, for just for the free turbine, and divided by the calorific value of the fuel
Yes.
into fuel flow rate, right? So that is the efficiency. So for the free turbine, then we need to find out the net work output. To do that, how will we proceed next? What will be the next step?
Pressure at 04 should be known.
Pressure at 04 should be known. Otherwise, if it is not known, what is the difficulty?
T05 exit temperature is unknown.
Yes. So we need to calculate. So how will we calculate T05?
So exit pressure is known. From the pressure ratio, T05s can be known.
Correct. Good.
From the efficiency, isentropic efficiency, we can know T05.
Correct. So we need to know P04. How will we find P04?
So again from T03 and T04s.
T04s. So first we have to find T04s then, because at this point we know T04, right? So that's why we need to use the efficiency of the turbine. Correct. Your answers are all correct. Good. So efficiency of the turbine is 0.89, 89%. So using the definition of efficiency for a turbine, efficiency is equal to T03 minus T04 is the actual work output by the ideal work output, which is T03 minus T04s. So in this equation, T03 is 1380, it is known. T04 is, we just have calculated right now, 1132.699 Kelvin. And again, T03 is 1380 and T04s is unknown. So we can find out T04s, which is 1102.134 Kelvin. So once we know T04s, all the steps are what you have just said. So P03 by P04 is equal to T03 by T04s to the power gamma g by gamma g minus 1, where gamma g is the gamma of gas, which we will take as 1.333. Okay, from this point onward in the course. So this gives us T03, we have already know, T04s we have calculated just now. So everything is known on the right hand side. T03 we know it was 911 point something we had calculated, right? 911.7. So this gives us P04, which is equal to 370.663 kilopascal. Okay. So the pressure has decreased from 911 to about 9 atmospheric pressure. Pressure has decreased from 9 atmospheric pressure to somewhere around say 3.5 atmospheric pressure. And the rest of the expansion from 3.5 atmospheric pressure to 1.2 atmospheric pressure, that will occur in the next turbine. So P04 is now, it has been obtained. So now we can go for the calculation of the free turbine. So we will first find T05s. Okay. So T04 by T05s is equal to P04 by P05 for the isentropic relation, using the isentropic relation, to the power gamma g minus 1 by gamma g. Okay. P04 we have just now calculated 370.663. P05 is given 120 kilopascal. Something is bugging me here. Anyway, let us continue. Can you still hear me? Hello? Can you still hear me?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay. So P04 by P05 is known. So we can find out the temperature ratio, which is 1.3254. So because T04 we have already calculated to be equal to 1132.699 Kelvin, we can find T05S, which is 854.588 Kelvin. Okay, this is the ideal temperature at the turbine outlet exit if there was no losses. But because of losses, we need to calculate the actual temperature using the isentropic efficiency of the free turbine, which is also given as 89%. Again, by definition, T04 minus T05 by T04 minus T05S is equal to 89.89, sorry. So we find T05 to be 885.1802 Kelvin. So all these are realistic values. So you can see that quite a bit of energy is actually lost. Okay, quite a bit of energy is actually lost to the atmosphere. So 885 means how much? It is more than 600 degrees centigrade. Okay, so we could have gone slightly lower up to atmospheric pressure, but you cannot go below that. So always T05 will be much higher than atmospheric temperature, right? Because even if it is at the constant pressure line, this point will be much higher always. So always there is lot of energy that is lost unless we use a regenerator to recover some part of the energy. But in this case, we could have recovered because T02 is much less than T05, although our diagram shows differently. But what we have calculated finally, T02 is 570 something. I forgot the value. 577 and T05 is 885. So we could have used a regenerator because T02 is less than T05. Anyway, in this problem there is no regeneration. So the net work output then is the work output from the free turbine. Okay. So we have already obtained all the temperatures. Now we can calculate all the necessary parameters, right? Performance parameters. So work output, specific work output means work output per unit mass. Always remember to use the correct symbols. Small letters is for specific work, anything specific. Okay, means per unit mass, and capital letters is for the total work output, means power output. Okay, m dot into W net. So generally we calculate in terms of per unit mass. Okay, so per unit mass, this is equal to 1 plus F, which is the mass flow rate in the free turbine, per unit mass of air at the inlet, into Cp of gas into T04 minus T05. So this is equal to, so this 1 plus F is 1.0245, CPG is 1.148, T04 we have calculated to be equal to 1132.699 Kelvin, and T05 we have calculated as 885.1802 Kelvin. Always calculate minimum up to 3 digits. I recommend up to 4 digits, okay, but minimum up to 3 digits. If you just calculate up to 1 digit, at some point you will introduce significant error and your answer will be wrong. Okay, so that type of mistake should not. For example, if you round this off to 0.025, you will get a completely wrong answer because 0.025 is completely different from 0.0245, and all the results will be significantly different because you can see the difference. It will lead to a large amount of difference. Okay, more than 2% difference will be there in the answer. 2% is a large amount. So anyway, so the net work output, what we can calculate is comes out to be 291.113 kilojoule per kg. Okay, this is the net work output from the net specific work output from the cycle. Now the efficiency is the net specific work output, which is the net work output basically divided by the energy which goes per unit mass flow rate of air, which goes into the, which we are providing, right? So which is equal to mass flow rate of fuel per unit mass flow rate of air, which is F, into calorific value of fuel. Okay, so F into QCV. So 291.113 divided by 0.0245 into 43,000 kilojoule per kg, it was given. So we find that this is equal to 27.63. It is actually quite less, okay, from an ideal cycle. But an ideal cycle, what will be the value? then can somebody calculate quickly and tell me what will be the value of thermal efficiency for an ideal cycle? What will be the value for an ideal cycle? Calculate. What was the expression? 1 minus 1 by r to the power gamma minus 1 by gamma, right? What is the expression of efficiency of a simple cycle? This is a simple cycle, right? Similar to a simple cycle, because it's a continuous, means we can consider it to be a continuous turbine process. R is 9.
%.
Is it 42? For me, it's coming as 46%.
Yes, I had used the gamma gas. No,
No. For ideal, you have to use everything ideal. So it is ideal, yes. Okay. Ideal cycle. Everything is like the ideal assumptions. So for ideal cycles, we use, these are also known as air standard cycles. So we use air properties. Okay. For ideal cycles. So it is coming as 46.6. So you can see that how much in real life, how much reduction occurs, all using realistic values only. And we even have not considered the pressure loss, which will lead to even 1% maybe decrease, because turbine work will decrease by that amount. Okay. So typically the values will be higher because nowadays we use larger compression ratio, not 9, 20 or around 20. So, but for this type of value, you can see that it is quite less. So finally, specific fuel consumption. By definition, again, if you remember, it is the fuel consumption per unit power output. Okay, so which is m dot f by capital W net, which is also equal to then f by small w net. Okay, so 0.0245 by 291.113. What is the unit? What will be the unit? F does not have any unit. W net will have kilojoule per kg, right? So the unit is kg per kilojoule, or we can write this as kg per kilowatt second. So this comes out to be 8.416 into 10 to the power minus 5 kg per kilowatt second. Why we have converted to kilowatt second? Because we want to convert it to kilowatt hour, because that gives us a more practical value. So this is equal to this value into 3600 kg per kilowatt hour. So which comes out to be 0.302 kg per kilowatt hour. Why this is more practical? Because you know, let's say if I need a turbine of 100 kilowatts, and if I need to run that turbine for 1 hour, how much fuel will be required? Directly we can say from here, right? So if I need, so for 1 kilowatt turbine, in 1 hour I need 0.3 kg fuel. So for 100 kilowatt turbine, I will need 30.2 kg of fuel per hour, right? So if I need to run it for 10 hours, I will need 300 kg of fuel. So like this, we can easily calculate. Something is wrong in the calculation, or can you check this calculation? Is it coming correct? Let us check. 8.416 into 10 to the power minus 5. I think it is correct. And 303. It is correct only. Okay. So any questions on, you should be able to solve similar type of problems. Okay. go through the problems that I have seen on real cycles. Ideal cycles, you can look up the problems from the book, any book. Okay, ideal cycles, it is much easy to solve. So there is nothing much there. For real cycles, if you follow step by step, you will be able to solve the problems. There is nothing tricky or no tricks are there. It is just simple, say, step by step process based on simple understanding of the cycle. If you can draw the cycle, that is sufficient. Then you can solve the problem. So, and in the exams, you can means more amount of problems will be there, less theory. Okay, as I have said, because this is more like a numerical exam. So, if there are no questions, let us move ahead. Okay, so we have almost finished this part. What I'm going to do is, we are going to see a few comparisons. Okay, like we have done for the ideal cycles, but not all the cases we will do, because here the number of variables is so many. Like, for example, the compressor efficiency can change, the turbine efficiency can change. Obviously, some of the things you can predict just by intuition, that if the compressor efficiency decreases, overall efficiency will decrease, overall work output will decrease. So some of these are very easy to understand. If the turbine efficiency decreases, overall work output will decrease, overall efficiency of the cycle will decrease. So similarly, there are other parameters also now. Ambient temperature, all these parameters also may influence. Okay, then the pressure losses in the regenerator is means in the regenerator air side and in the regenerator gas side. Then the pressure loss in the combustion chamber efficiency, transmission efficiency, all of the things can change. So we will see for one or two cases, and you can obviously write your own programs. So for these cases, we need to write programs because you cannot do simple algebraic calculations in terms of like we cannot derive expressions because so many variables are there. We cannot derive expressions, so we have to write simple programs to find out the values. Let us take a look at one or two cases. I will show you for the regenerator and the simple Brayton cycle, and means simple Brayton cycle and the simple Brayton cycle with regeneration for real cases, how the efficiency change. I have already uploaded these programs in the portal. Okay, you can take a look later on. So you can go to the codes, and for efficiency you can run this in MATLAB, and for net work output you can run this in MATLAB. Okay, based on today's discussion, you will understand what is there. I have not made any comments inside the code. It is just written in a dry form. Anyway, let us see. Okay, let us try to understand. So this is the, I hope you can see the, can you see the plot?
Yes, sir.
Okay, so this is the efficiency plot versus compressor pressure ratio. Okay, for a ideal cycle. We have already seen this. I've just plotted it again just to show you the. Just a second. So just to show you the comparison, I have plotted it again. This is for the ideal cycle. Okay. Now for the ideal cycle, if you remember, for the simple Brayton cycle, the efficiency is only the function of R. If we consider that gamma is not changing, it is only the function of R. Okay. There is nothing else that matters. Means, for example, the temperature ratio does not matter. But we will see that for a real cycle, the temperature ratio also affects the efficiency. Okay. So this is only consider this part. Okay, this is a spurious result because they once after this point there is we cannot get any work output from the cycle. So all this is just spurious result based on extra calculation. So we can ignore this part. So what happens is that this is for temperature ratio of 2. Okay. So if for example, if the inlet temperature is 300 Kelvin and the maximum temperature is 600 Kelvin, we will obtain something like that. Obviously, nowadays nobody uses maximum temperature of 600 Kelvin, which is very, very less, right? Relatively. But we can see that maximum efficiency would have been only very less, 5%. And then quickly it will go to 0. Okay, quickly it will go to 0 at about slightly higher compression ratio of 4. So this is for T equal to 3. Okay. Still you can see that much less than the ideal cycle. Then T equal to 4, T equal to 5. So what we see is that if you ignore this this line, T equal to 2 line. So what we see is that for all these cases, means for the real cycle, the first observation is what? That the efficiency is much less than the ideal cycle. Okay. The next observation is that the efficiency increases and after some time it will decrease. Even for this case also, after some time it will decrease and it will go to 0 at some point. Okay. So there is a optimum value of compression ratio at which the efficiency is highest. Okay. This is our second observation. And then what we also see is that with increasing temperature ratio, means the increasing turbine inlet temperature, the efficiency is higher, unlike the ideal cycle, where the turbine inlet temperature did not play any role. Here, which say, for example, if the inlet means the ambient temperature is 300 Kelvin and the turbine inlet temperature is 1500 Kelvin, which corresponds to T equal to 5, we can see that the efficiency is much higher, higher than 30%. But if it is, say, only 900 Kelvin, it is around 20% peak efficiency, around 20%. Okay, so much less. So this is another observation. Then what we also see is that the optimum value at which the maximum efficiency is obtained shifts towards the right hand side, and there's a large flat region over which the efficiency is almost does not vary much, at least for the higher temperature ratios. We can see a large region, means we have some flexibility of taking the value of R. So we can take, so for example, if T is 5, means if the temperature ratio is 5, it will not matter much if we take R is as 20 instead of 30. So efficiency will be almost similar, but less compression ratio means that less number of compressor stages, less number of turbine stages, less bulky, so less weight, okay, and less cost. So similarly, if we take R15, then also there is not much decrease in efficiency. So even 15 will also work out nicely. Okay. So these are some observations. So why this occurs? So for example, why the what happens at higher compression ratio? What happens at higher compression ratio for a real cycle? The compressor is not 100% efficient, right? So for higher compression ratio, the work input to the compressor will increase. And if the compressor is not 100% efficient, the losses will also increase. And at one point, what will happen? The losses will become larger than whatever gain is obtained by increasing compression ratio. Okay, whatever gain. So ultimately, the efficiency again goes down. Okay, so that is why there is an optimum point. Unlike ideal cycle, where always you can keep on increasing and it will go on increasing. The efficiency will go on increasing. But in this case, it will not happen. The turbine work output will not be able to compensate for the increasing losses in the compressor, because in the turbine also there will be large amount of losses, right, with increasing ratio, increasing pressure ratio. However, if we increase the temperature of the turbine inlet, there is more work output available from the turbine, because now we have a larger delta T in the turbine for gaining work. So relative to the work output from the turbine, the losses become less significant. So as a result, for larger value of T, we still get quite good efficiency. Okay, but for smaller value of temperature ratio, the work output from the turbine is very small. I hope you are understanding this. Please ask me question if you don't understand. Okay, so this we have to use logic to find out all this relation. So for lower temperature, at the turbine inlet, the temperature range of the turbine means the change in temperature in the turbine for work output will be less. As a result, relatively the losses is quite high. Okay, so that is why quickly the efficiency goes to zero. So nowadays we can go to larger than t equal to 4 or even to t equal to 5. Okay, for aerospace even greater than that, we can go up to t equal to 6. For industrial turbines, we generally are around t equal to 4 or 5 between something. So what was our value in the problem? We have just solved the problem today, right? Our values were, what was the value of small t temperature ratio for our case? 1380 by 288. Okay. 1380 by 288. Let us use the calculator. I don't want to stop the.
So 4.8.
4.8. Okay, good. So, and compression ratio is around 9. It was 9, right? So 9 maybe somewhere around here, right? And 4.8 will be somewhere around here. Okay. So say somewhere around here at this point. So slightly less than 30%, maybe 27, 28%. Okay, if you go like this, slightly somewhere around here. So, and that is what we have also obtained from our calculation, right? We have obtained water efficiency 27.63%. So you can find also from here. Okay. And so what else observations are there? I have noted them down. So eta becomes a function of T and RC. Peak value of eta occurs at a particular compression ratio. Peak value occurs at a particular compression ratio, as we have seen. Peak specific work we have not yet seen. We will see later. Okay. Curves are flat near the peak. Okay, that also we have seen. For the work also we will see later. Then we'll come back to this point. Okay, and work output and efficiency. So just now we are just looking at efficiency. So efficiency increases with higher turbine inlet temperature that we have seen. Okay, and the optimum value of RC also increases. And I have described why this happens. Okay, because of more work output relative to the losses. So ambient temperature we have not yet discussed. We will see. Okay. So this is for the simple Brayton cycle. Okay, so what happens for the regenerative cycle? Let us see. These are the ideal. If you remember the ideal cases for regenerative Brayton cycle, the efficiency was function of temperature ratio and pressure ratio, and it followed the opposite pattern. It started from a very high value and then decreased. So for low compressor pressure ratios, we had very high efficiency. For higher compressor pressure ratios, the efficiency went below the simple Brayton cycle efficiency. What was the reason for this?
Energy input through regenerator decreases.
Correct. Because this, why that decreases?
Temperatures get closer. The
Correct. Temperature of the compressor means compressor exit temperature increases with higher compression ratio. So it gets closer to the turbine exit temperature. And at one point, it will become equal to the turbine exit temperature. And at that point, this is the point, it will be equal to, because there will be no regeneration, it will be equal to simple Brayton cycle efficiency. And after this, what will happen? Heat will flow in the opposite direction in the heat exchanger. So the exhaust gases will have a lower temperature as compared to the compressor exit temperature, and that will result in opposite direction heat flow. So which will decrease the efficiency even further. So this is for T equal to 2, 3, 4, 5. This we have already seen. Okay. So these crossover points, how this crosses. Okay. So this is, so now we'll see for the real cycle with regenerator. Okay. So this green line. In this green. So we'll see that the behavior is totally different. Okay. What are the observations from here? One is that it goes to 0 at some point. Okay, I may have wrongly written to be 1, but it does not go to 0 at 1. It goes to 0 at a certain point, at low pressure ratios also, and at high pressure ratios also, and there is a peak value. Okay, unlike the ideal cycle where at pressure ratio 1 we were getting the highest efficiency, here it goes to 0. What happens is that even if before you go to pressure ratio of 1, near to the pressure ratio of 1, whatever work is generated by the turbine, okay, is entirely used up by the compressor. Because of losses in the turbine work output becomes equal to the compressor work input. However, still there is some input still you need some heat addition. So the efficiency becomes equal to 0, which is the net work output, by the heat addition. So it becomes efficiency becomes equal to 0. But in ideal cases, what was the case? Uh, at R equal to 1, the temperature, the turbine work output is equal to the compressor work input. So work output is 0, net work output. But the heat input is also 0. So it becomes undefined. But if you actually mathematically solve it, you will find that at the limit, the efficiency has a non-zero value, very high value. Okay. Although the work output is 0, but the heat input also is 0. Okay. But at the limit, we find that the efficiency is high. But in real cycles, that does not happen. So the efficiency increases quickly and then it decreases again. Okay, T equal to 2, 3, 4, 5. So you can see that again there are crossover points. So for example, for T equal to 4, which is more realistic value, we see that is around say 10 or 11, something like that, right? $10.7. So at around 11, 10.7 compression ratio, after that the simple Brayton cycle becomes no. This should be the point, right? Because we are looking at T equal to 4. Okay, crossover point is 13, around 13. So after 13, the simple Brayton cycle is more efficient. Before 13, the regenerative cycle is more efficient. Similarly, for T equal to 5, we find that around 20 or 21. After that, the simple cycle is more efficient. Before that, the regenerative cycle is more efficient. Okay. So, and there is a peak value which occurs at a very low compression ratio. Okay. So, for regenerative cycle, eta versus pressure ratio curves are totally different from ideal regenerative cycle. Eta goes to 0. Okay, not at RC equal to 1. This is wrong. Near to RC equal to 1. Okay. Near RC equal to 1. Just note this. Oh, we have anyway not added. And the peak value is higher than that of simple Brayton cycle. That also we've seen the peak value is higher, right? Work output we will see now. Okay, so efficiency related, any question is there? I am not showing the other plots. You can try on your own. Okay, for the reheat cycle, or maybe I will give as an assignment for the. I will give assignment for the jet engines because that is more interesting. Okay. Means computer programming assignment for the jet engines, not for industrial turbine. But if you want, you can try on your own for the reheat cycle and the intercooled cycle. But those are not used much. Later we will discuss that. Only the simple Brayton cycle is very widely used, and sometimes the regeneration cycle is used. For practical purposes, the reheat cycle is not used much, and the intercooled cycle is also not used much. Any questions, or is this clear? Anyway, you have the program. You can run it on your own and check. Okay, for different values, you can change the, for example, you can change the efficiency of the isentropic efficiency of the compressor and turbine and see how this efficiency changes of the cycle. Or you can change the, so let me show you what values I have taken in this case. So what we have taken values, what values we have taken are, so anyway, gamma and these are what we have already discussed, but compressor compressor efficiency as 85%. Okay, slightly different I have taken from the problem that we have solved. If you use those values, you will get slightly different value. Turbine efficiency I have taken 87%. Okay, and mechanical efficiency 99%, combustion efficiency 98%. Gamma of gas anyway you know, Cp of air, Cp of gas you know. Inlet temperature I have taken as 288 Kelvin. Inlet pressure is 1 atmospheric pressure. Then if there is a regenerator, then the pressure loss in the regenerator is of 3% of the compressor pressure outlet, compressor outlet pressure, sorry. And in the gas side, I have taken 0.04 atmosphere pressure loss. And in the combustion chamber, the pressure loss I have taken 2% of compressor exit pressure. And regenerator effectiveness I have taken 90%. You can take 80%, you can see what will happen. Efficiency will decrease significantly. Okay, and calorific value also realistically you have taken 43,100 kilojoule per kg. So you can play around and check what will happen with other values. Okay, how the efficiency changes. But what we see is that there's a drastic drop in efficiency. Okay, from ideal cycle. Even for the regeneration cycle, you can see compared to the red curves, the green curves are much lower, right? Much lower. So T equal to 5 and this T equal to 5, around 20% difference is there in the efficiency. 20% means there's a jump of 20 points basically. So percentage wise, there is much lower efficiency. Okay. So let us look at the work output. Again, using, I hope the same values are there. 85, 87, 99, 98. Yes. Same values. Okay. So these are for real cycle system. Here I have not plotted for that ideal cycle. Ideal cycle will be much higher. So for real cycle, the work output decreases. Follows a similar pattern, but it quickly goes to 0. So for T equal to 2, it goes to 0. At very quickly we have seen efficiency becomes 0. For T equal to 3, it goes to 0 here. T equal to 4 and T equal to 5. Okay. This is in kilojoule per kg on the left hand side. And in the previous case also, ideal cycle also, it was dependent on temperature ratio and pressure ratio. Here also it is dependent on those, but it is much lower. You can compare on your own later on. And if there is a regenerator, the work output is slightly decreased. Okay. In the ideal cycle, what was the effect of the regenerator on the work output? Ideal cycle, what was the effect of regenerator on the work output? You don't study at all before the exams. This is
no effect, sir.
No effect was there. No effect was there. But in this case, there is effect. Why this is happening?
So maybe
There's
due to pressure loss.
Yes, correct. Good. There's a pressure loss which reduces the turbine work output. Turbine inlet pressure is reduced. So the pressure ratio of the turbine is less than the pressure ratio of the compressor. So turbine work output is decreased. Okay. So the work output is so the specific work output decreases. Okay. You can play around with the pressure losses. So for example, if you remember this, I cannot draw on the same plot right now, or it should be possible to draw by let me check. A very large, absurdly large value. Let us take right here. will be slightly lower. Okay, but the effect of pressure loss is still not, obviously there is quite a bit of effect, but not as much as, means, because the pressure loss is not, cannot be very high, right? It cannot be 50%. It can be 4-5%, 4%, 5%. So it slightly reduces the work output. So I have taken here a pressure loss of 10%, but still you see that it is not as significant. Okay, go back to the original one. And the other thing is that for both the ideal and regenerative cycle, for both the simple Brayton and regenerative cycle, the work output increases and then up to a certain optimum point and then goes down. And there is a large flat region. Okay, large flat region means flat. It's not obviously flat, but it is somewhat flatter. So anywhere we can operate based on the optimum efficiency and optimum RC for work output, we can operate. We can select a value of pressure ratio so that we get quite high efficiency also and quite high work output also. Okay, so the peak value for work output is different from the peak value for efficiency. Okay, that is difficult to see, but that is the case. How many times I have pressed? Fine. Okay. So then let us summarize this entire part of real cycles. Okay. Then we will take a break. And, so for simple Brayton cycle, we have seen already the effects of efficiency. Efficiency is a function of T and RC. Peak value of efficiency occurs at a particular RC. Peak specific work output, we have now seen that it occurs at a different value of RC. And if you see, it will be lower than that for maximum eta. Okay, we could have seen that. So in between we can, so the curve is nearly flat in between near the peak. So any pressure ratio in between these two optimum values can be used without too much loss of efficiency and getting good work output also. Okay, what is typically chosen is the lowest pressure ratio, which is still acceptable because it reduces the number of compressor and turbine stages, and also it avoids, if the pressure ratio is less, it avoids excessively small blades at the high pressure end of the compressor. Okay, and relatively the losses will be large if you have very small blade. Okay. Work output and efficiency increases with higher turbine inlet temperature. That also we have seen, and the optimum value of RC also increase with higher turbine inlet temperature, that we have seen. Okay, one thing I have not shown here, you can try on your own, is but it's nothing to try also. It's just intuitively you can understand. If the ambient temperature increases, the efficiency and work output decreases. If the ambient temperature increases, keeping the turbine inlet temperature same, the temperature ratio decreases, right? So instead of say 288, if I have 313 at the turbine as the ambient temperature, for the same outlet, for the same turbine inlet temperature, the temperature ratio will be lower. I mean, Tmax by T ambient, that will be lower. And as a result, we have seen that for lower value of temperature ratio, the efficiency and work output both are lower. So we'll get quite like the ambient temperature also plays a part. Okay, lower the ambient temperature, higher will be the efficiency and work output. Now for the regenerative cycle, what we have seen, efficiency versus RC curves are totally different. Okay, so it goes to 0 near RC equal to 1, not at RC equal to 1. Okay, this is, just strike it out. Unlike ideal cycles, the peak value of eta is higher than the simple Brayton cycle. Okay, that also we have seen, and occurs at a lower value of RC as compared to the simple Brayton cycle, obviously. And specific work output slightly reduces due to pressure drop in the regenerator. Increase in regenerator effectiveness, we have not seen this, but you can try this on your own, will reduce the optimum value of RC and eta will increase. Okay, obviously eta will increase if you increase the regenerator effectiveness. Means more regenerator effectiveness means that more efficient heat exchange. So more energy will be recovered and efficiency will increase. Okay. So for reheat and the intercool cycle, I have not shown, but what happens I will just describe quickly, specify quickly. So for reheat cycle, the specific work output is increased. Increase means as compared to the simple cycle. Okay, as compared to the ideal cycle, obviously it will decrease. Because of higher pressure losses, because you have the second part, reheating part, more pressure losses, efficiency is lower. Okay, and efficiency is lower as compared to the simple Brayton cycle. It is similar to the ideal cases. Okay, and practical problems due to, so this is a very important point, okay, which we have not previously discussed. What happens is that if you have reheating, right, so your turbine outlet temperature for the same outlet pressure increases. Okay, turbine outlet temperature for the same outlet pressure will increase because you are going more towards the right hand side of the TS diagram. So the turbine outlet temperature will increase. What is happening is that say if you have a reheat, you will go like this, somewhat like this. So instead of ending here, you will end somewhere around here. So at a higher point, okay, on this blue line. So as a result, for the same pressure, you will have a higher temperature. So the density will be lower. Higher temperature, pressure is same, density will be lower. Density lower means other way of saying this is specific volume is higher. So it leads to you need more cross-sectional area for the same mass flow rate. So the blades will become excessively long. Okay. And that means that if blades are excessively long, you know that it will lead to more stresses. So you have to keep the RPM lower. So all these are related, right? So that is a practical problem. So that's why reheat is not used. And you also need reheat and for reheating you need additional combustion chamber, right? So it can, and efficiency is also lower. Okay. Ultimately, it is not giving us much except improved work output. Okay. So it only makes sense to use reheating when it can be combined with a regenerator so that you can get higher efficiency. Although for the real case, still the efficiency will be much lower than the ideal case. So this is not used much in real life. Same story for the intercooled cycle. Although the problems are little less, like this type of practical problem is not there. But there is another practical problem for the intercooled cycle that we had already discussed. The self-contained nature of the gas turbine is lost. Means now you need a heat exchanger where you need to supply cooling water. So it is not anymore a self-contained device. You need some source of water constantly for cooling for the intercooler, and system becomes very bulky because you need a large heat exchanger for intercooling. Okay, so again, this is not used much. So ultimately, what is used nowadays? So these things were developed. If you think logically, or if you remember, these were developed long time back actually. So initially, say 80, 90 years ago, the efficiencies of gas turbine or efficiencies of turbines used to be much lower. Okay, larger frictional losses, less pressure ratio. So efficiency was lower, and maximum temperature that could be obtained was lower. That actually limited the efficiency because turbine blade material was not good. So ultimately, other ways needed to be used to increase the efficiency. But nowadays, with much better manufacturing processes, much better designs, much better cooling effect, all these additional devices are not required. The simple cycle, we can achieve a very high compressor pressure ratio, and as a result, we can achieve a very high turbine inlet temperature. So the simple cycles itself are very efficient, and in most cases, they are more than sufficient. Okay, in some cases, it makes sense to use also regeneration cycle to get very high efficiencies. So nowadays, what are used? Either simple cycles with very high compressor pressure ratio, say around 20, or very low compressor pressure ratio, say around 5, 6. regenerative cycles. Okay, the other two are not used too much. Although it is important to know that in theory they can be used to increase the efficiency in work output, or increase the work output, not the efficiency at the cost of efficiency. In real life, it's a different scenario, and this will become particularly important for the next part what we study, which is the jet engines, because in jet engines the mass of the system, weight of the system becomes a very important factor. You want the system to be as less in size as possible, because you have to carry that additional weight, and so we need to simplify the cycle as much as possible. So for those cases, only simple, all the jet engines are based on simple Brayton cycle only. So we'll take a break and we'll go into the next topic. So this part is finished. I will just start today I will just start and we'll go through some calculations or some discussion on turbojet engine, on jet engines. Okay, after this break. Any questions? So let us take a break then. Yes, Nikhilesh, you are asking something, or?
Yes.
Okay, so we'll continue. So please, if you want, you can, means I suggest that you go through those programs, means you don't have to go through them, but run a few cases to understand how the behavior occurs. Can you hear me still? Just confirm once.
Yes, sir.
Okay. So you can run a few cases just for your own interest. You will means to see how the different things vary. You can even write your own programs, means make modifications to see the effect of reheating, or just using the codes that I have given. You can see the effect of ambient temperature, effect of, say, just by varying one parameter. The compressor efficiency is varied. Everything else is same. What is the effect of on net efficiency of the cycle? If the turbine efficiency varies, what is the effect on net efficiency of the cycle? Things like that you can play around with. Okay, to get a better understanding and think logically then why this is happening. Some of the things are very easy to understand. Some of the things may be slightly more complicated. Anyway, so we will move on to the next part of the course, which is on jet engines. And it's quite interesting, this jet engines topic. And what we will do is we will go through 4 or 5 different types of engines over the next many weeks. Means obviously we will start now today. And Thursday there is no class, but Friday's class will still be there. And then after the exam, for the means at least 3-4 weeks it will take, and then towards the second half of the final part of the session, means of this course, we will discuss about the different components in slightly less detail. Different components mean individually about the compressor, about the how the design of the compressor works, how the design of the turbine, and slightly about the combustion chamber. Okay, so we'll take up all these 5 types of jet propulsion cycles in this course, starting from turbojet. Then we'll go into turbofan, turboprop, and briefly ramjet and pulse jet, okay, which are easy to study because the cycles are much simpler. Other types of aircraft propulsion devices we have discussed in the beginning of the course. Initially, can also be used, obviously, but rockets are very means very inefficient in the sense that you have to carry your own fuel, and they do not scale well with increasing weight. So to increase the payload, you need to drastically increase the amount of fuel that is required. And there is no necessity of using rockets because in the atmosphere anyway air is there, so you don't need to carry your own oxidizer. So what we will do is we will start this turbojet part, and then we, not today, but in the next classes, we will define a few things about jet engines, like performance parameters, which are slightly different from industrial gas turbines. So industrial gas turbines, the main 2 main things were important: the efficiency, 3 things you can say: the specific fuel consumption, which we calculated as per unit work, what is the fuel consumption, and the work output, net specific work output. For jet engines, efficiency is obviously very important still, but instead of work output, thrust is the more important factor. So what is the specific thrust or impulse? Specific thrust is known as impulse. That we will see how to calculate, and what is the fuel required per unit thrust, not per unit work. So thrust specific fuel consumption, that also we will see how to calculate. And we will also define other types of efficiency. So not only this thermal efficiency, but there is another efficiency known as propulsive efficiency, which plays a very important role. Okay, so that also we will see. So all these things. But today, let us first. So instead of directly jumping into those performance parameters, I feel that it is best in this course to first study about one of the cycles, a turbojet, and then go into the performance parameter, and then go on with the other cycles. Okay, other types of devices. So turbojet, if you remember in the beginning of the course, we had discussed what is a turbojet. So it is one of the basic forms of jet engine. where you have a gas turbine, basically similar to an industrial gas turbine at its core. So you have a compressor, multiple stages of compressor. In industrial gas turbines also we have multiple stages of compressor. Similarly, we have multiple stages of compressor to increase the pressure ratio by around 20 or higher value. And to run the compressor, we have turbines. Okay. So in this case, we do not need any extra work output. So we only have sufficient amount of turbine stages just so that we can run the compressor. And we don't need to expand the air in the turbine up to the atmospheric pressure. Okay. So only sufficient amount of work is required so that we can run the compressor. So after the turbine, till the combustion products will have large amount of energy and still the pressure will be quite high. So rest of the expansion occurs in a nozzle. So from this relatively high pressure to the atmospheric pressure. So in this expansion process, what happens? The enthalpy that is there in the fluid, means the high temperature, high pressure fluid, reduces its enthalpy and increases its kinetic energy. So ultimately, you get very high velocity exhaust from the at the outlet of the nozzle, and this high velocity exhaust is necessary to provide thrust, because thrust depends on the change in momentum. So the momentum at the exit minus the momentum at the inlet. Okay. So as a result, we use a nozzle here. And in between, obviously, we have combustion chambers or one combustion chamber or multiple combustion chambers to where the fuel is injected and combustion occurs to increase the temperature so that we can get work output from the turbine. At the inlet, unlike industrial gas turbines, before the compressor, there is another region. It is not shown here clearly. Okay, I think I have shown you for the turbo fan like this. So this part, it is not clear from here, but this is very carefully designed. Okay, slightly, the area is slightly increasing as you go inside. So this is actually a diffuser. Okay, so a diffuser is there before the compressor. So in this case, this is a turbo fan, there is a fan, but for a turbojet, there will be a diffuser. Diffuser is similar, exactly opposite of a nozzle. Okay, so you get high velocity at the inlet. Unlike industrial gas turbines, the jet engine is flying itself. It is flying at very high velocity, around the speed of sound. So around say 900 km/h or 1000 km/h speed. So or even larger turbojets. Nowadays, military aircraft use turbojets. So turbojets operate at Mach 2, Mach 1.5, around those speeds. Okay. Supersonic speeds. At subsonic speeds, nowadays we don't use turbojet because the propulsive efficiency is less for turbojet. Okay. So at those situations, the velocity is very high. So we have a large amount of energy itself available with the fluid because of its high velocity relative to the engine. So that energy can be recovered, that kinetic energy can be recovered by converting that kinetic energy into enthalpy. So by slowly expanding it in a diffuser. Okay. So in a diffuser, exactly opposite to a nozzle, the pressure increases smoothly and the temperature increases smoothly and the velocity decreases. Okay. And there can be either axial flow compressors like this. Axial flow compressors are like your fans. Okay, the flow comes in axially and goes out in the other direction axially, and similar to a fan. So if you consider an exhaust fan, you will see curved blades. You provide some work input to the exhaust fan, right, in terms of electricity. So that actually results in increasing the pressure of the air as it moves from one side to the other side. Slight increase occurs. So in the compressor, the blades are more curved and more increase in pressure occurs in each stage. And with multiple stages, you get large increase in pressure. So there may be 10, 15 stages. Okay. So there can also be centrifugal compressor where the flow comes in axially but goes out in the radial direction. Okay. The advantage of centrifugal compressor is that you get much larger compression in a single stage. Okay, as compared to axial flow compressor. So less number of stages is required, but there are major disadvantages for a jet engine. One is that the cross-sectional area increases. Okay, as compared to the intake, the cross-sectional area is more. So this results in larger drag, and you want the drag to be as minimum as possible for an aircraft. Okay, so to improve the efficiency. So so this increases the drag as compared to this. So this is a big drawback. And another point is that this flow direction is not like not aligned to the combustion chamber direction. So you have to again move the flow in another direction to bring it to the combustion chamber. So this is not as simple say as an axial flow compressor. So nowadays all the jet engines that are used use axial flow compressors, axial compressors. Okay, but initial designs we had seen that the British design used centrifugal compressor during Second World War, and the German design used axial compressor. But nowadays all the aircrafts use axial compressors. And previously passenger aircrafts also used turbojets. If you maybe I will show you in the next class. I have to find some. So Concorde in was one example, but even other passenger aircrafts which flew at subsonic speed also use turbojet. So if you see very old aircrafts, okay, old passenger aircraft, you will see that the engine is very thin, okay, as compared to turbofan, because the cross-sectional area will be much thinner. When we study about turbofans, it will be clear that for turbofans, you have an outer section. We have discussed, I think, also briefly in the beginning of the course. This outer section is there, which increases the cross-sectional area. So turbofan engines are very large in size. Okay, turbojets are very thin and narrow. Okay, let me see whether we can find something. Turbojet. Okay, this one. Even better example should be there. This one is better. So you can see that basically it's a very small diagram, but the engine sizes used to be very thin and narrow. Okay, this actually there is a link between this and the incidents that occurred recently, means in the last few years, with what aircraft do you remember? Boeing 737 Max or something like that. That aircraft had to be grounded. Anyone remembers which aircraft was it? Like there were a couple of crashes because of the autopilot behaved erratically.
So 737 Max. There was a center of mass change from the original design.
Yes. So that is what I was going to explain. Is a good point. So for these planes were designed. So the 77 is an old plane. Okay, not the 77 Max. So the designs generally same design is used for many years. Okay, but what happens is that with time the engine efficiency increases because of better manufacturing processes. So you don't want to use the old engines. So you want to replace the engines. Okay. So at one point of time, it was seen that instead of using turbojet, if we use turbofan engine, it will be much better. Okay. So now this initial design, Boeing aircraft, was designed with a very low wing profile. Okay. So unlike Airbus aircrafts, low wing profile. Let me see, 737 picture is there or not. So say this one. So the wing is attached at a very low point in the body, not at a high point. Now, if you see it in an aircraft like new aircraft, you will see that the wing is attached at a high point, okay, somewhere just below the window. But here you can see the wing is attached at a very low point, and this was no problem. You can clearly see the turbojet engine here. This is a nice aircraft, a nice picture. You can see that it is very thin and narrow. okay, as compared to say this picture, right? So where it is very large in size. So when they tried to change the engine, so there was not much space below the aircraft wing to change the engine, okay, to turbofan, because turbofan cross sectional area will be much larger. So what they did was that they moved the engine forward. Okay, so 737 Max, if you see, the engine is moved forward. You can see it is not below the aircraft wing. It is moved much forward. Okay, so that it can be accommodated. Still, it is very low near the ground, but it is moved forward so that it can be accommodated. When the aircraft takes off, there is no issue. Okay, it does not. There is no strike. Okay, and there is sufficient space. So this actually changed the center of mass, as you have said correctly. So as a result, what they did was that used the software to control that, means to account for that change, and at means under very say rare circumstances, that software actually led to that means in I think 2 crashes were there, or I forgot how
So
many crashes.
angle of attack sensor was faulty, isn't that correct?
No, angle of attack sensor was faulty. That is true. But what happened is that uh, the autopilot tried to correct it instead of say like something related. I don't remember the exact.
So there was a stall that the computer detected, so that led to a dive. Computer
Yes, means it automatically led to a dive instead of say taking input from the
pilot.
pilots, right? So there was some bug in the. I think it is not only about the sensor. Because some checks were not there in the. Yes, you have to see if you go through the Wikipedia article, you will be able to find out most probably. I have read it long back, so I don't remember exactly. But all the 737 Max planes had a software issue, which in this particular type of situation resulted in a uh, wrong uh, uh, wrong decision from the autopilot instead of taking input from the pilot, like something like that. Exact thing I don't remember, but the main issue came from the design actually. If you study about this, you will see that it is related to the design of this uh, to the design of the 737 Max, where the turbojet was replaced by the turbofan, which resulted in this. So that's why all the 737 Maxes were grounded. In many countries, they were not used. Means many countries banned the use of 737 Max after this. Okay, recently only after changes to the software, some countries are again allowing the 737. I think in India recently the ban was lifted. Otherwise, all the 737 Max aircrafts were banned. Okay, so it is related to, means there is a lot of history behind this. It's very interesting, this tale. But there is a lot of history behind this. Means some decision taken long back can lead to some consequence which is very far away from it. Some totally different consequence. It's an interesting thing. You should read. Anyway, let us come back to this. We are digressing too much. So where were we? Okay. Turbojets, right? So now there are no passenger aircrafts generally which use turbojets because turbofans are much more efficient at the speed of the passenger aircraft. But for military aircraft, still turbojets are used for high velocity, high speed aircrafts. Okay. So we will take a look at how to do the calculations for turbojet. Okay. Where do we this one? Yes. So schematically, we draw the turbojet like this. Can you see the screen? Means the notes.
Yes, sir.
Okay. So schematically, we draw the turbojet like this. Okay. So we have the compressor similar to previously, and then there will be a combustion chamber. It is enclosed in the casing, and then there is a turbine. Okay, all on the same, mounted on the same shaft, and there is a nozzle and the diffuser section in the front. Okay. So if we draw the TS diagram for what is happening through the to the air which is passing through this and going out from the end as combustion products. So if we call the A as the ambient condition, okay. So some ambient condition, typically ambient condition during cruise flight will be around -50 degrees centigrade, okay, at those kind of altitude, and say around 0.2, 0.3 atmospheric pressure. Okay, so then and very high velocity. So Mach number here is around 0.9 for passenger aircraft. For turbojets, it will be more than 1. So maybe 1.5 or 2, something like that. So in the diffuser, there is it is a type of compression process. Okay, the air is compressed smoothly to a high pressure. So basically, the kinetic energy of the air is converted to enthalpy, high pressure and high temperature. So enthalpy increases means temperature also increases. And because this is not an ideal process, there is some frictional losses. So there is a pressure loss that happens. I will come into this in more details in a minute. But there is a pressure loss here. Okay. Ideally, we would have obtained a pressure of P0A, which is the stagnation pressure. But for an isentropic process, the stagnation pressure at the inlet. But because there is pressure loss because of friction, we obtain a slightly less pressure P01. Okay, and then we have the compressor stages. So from 01 to 02 is the compression process. 02s is the ideal state at the compressor exit. 02 is the actual state at the compressor exit. From 02 to 03 is the again similar to industrial turbines is the heat addition. I have not shown here pressure losses. There can be pressure. There will be slight pressure losses. Okay, in the combustion chamber. I have not shown here. So from 03 to 04, there is expansion in the turbine, and again the real state at the exit is 04. Ideal state would have been 04s, and then there is expansion in the nozzle from 04 to 5. So in the nozzle, basically the stagnation properties are not changing, but the enthalpy gets converted, static enthalpy gets converted to kinetic energy. The total enthalpy remains same, but the static enthalpy gets converted to kinetic energy. Okay, so we get very high velocity at the exit. And so that's why we are writing it in terms of static properties, 5. In ideally, it should have been at a temperature of 5s, but because of friction, we get a temperature of around 5, okay, T5. And the pressure may or may not be equal to atmospheric pressure at the exit of the nozzle. If the nozzle is not choked, we will study this later, what is choked nozzle and what is like non-choked nozzle. If the nozzle is not choked, means if the exit velocity is less than sonic velocity, then the nozzle will not be choked and the pressure will be equal to the atmospheric pressure. If the nozzle is choked, then the exit velocity is equal to the sonic velocity, and the exit velocity is equal to the sonic velocity, and accordingly the pressure at the exit also, means at the exit of the nozzle, will be also equal to the critical pressure. We will study what is critical pressure later on. Okay, critical pressure and critical temperature are the pressure and temperature at choked condition. Okay, and it will be higher than the atmospheric pressure, and so there will be a jump, there will be a jump directly at the exit of the nozzle. It is not a smooth change in pressure, so suddenly there will be a pressure drop at the exit of the nozzle from the choked condition to the atmospheric pressure. Okay. So this is how a turbojet cycle looks like in a TS diagram. Okay. Any questions? One question from my side, not related to turbojet, but in general. So if I use a conversion nozzle, I think I have discussed already, but again, let us recap, okay, revise. And it is operating at choked condition, okay. So maximum velocity that I can, if I use a conversion nozzle, maximum velocity that I can obtain is equal to the sonic velocity at the exit. So that will occur if the velocity means if the nozzle operates at choked condition. Okay. So can the aircraft fly at supersonic velocity with the nozzle at choked condition?
No, sir. We have to use convergent divergent for that.
It is not correct. Why is it not correct? Means it's good that you have answered, but it is not correct. What can be the reason? Means it can fly at supersonic velocity with a convergent nozzle. How is it possible, or why is it possible? So most of the turbojets use supersonic convergent nozzle, because designing a convergent divergent nozzle is very difficult, because you need variable cross-sectional area. Even for the convergent nozzle, you need variable cross-sectional area to account for different mass flow rate. Remember, you don't have any control on the mass flow rate directly, right? Because if the aircraft flies faster, there will be more mass flow rate. If the aircraft flies slower, there will be less mass flow rate at the intake. So accordingly, you should change the cross-sectional area of the nozzle outlet. So designing a convergent nozzle with variable cross-sectional area is much easier as compared to designing a convergent divergent nozzle. So only in very high-speed aircrafts, the convergent divergent, like a ramjet or scramjet, it makes sense to use a convergent divergent nozzle. Otherwise, military aircrafts operate with convergent nozzle only. So then, how is it possible to go supersonic with convergent nozzle? Any answers? This supersonic aircraft, how is it defined? Means when we will call it supersonic, if the speed is greater than the speed of sound. Speed of sound at what temperature? Speed of sound will vary with temperature or not?
Yes, sir.
It is at ambient means.
It is at ambient temperature, right? Speed of sound is equal to root over gamma RT. But if the T changes, obviously if the T increases, speed of sound will increase. So when we say supersonic aircraft, it is with respect to the speed of sound at ambient condition. Now ambient temperature is much less, right, as compared to the temperature at the nozzle exit. So what will be the speed of sound at the nozzle exit? It will be much higher as compared to the speed of sound in the ambient condition. So although the nozzle exit is at sonic speed, the speed itself is much larger than the speed of sound in the ambient condition. As a result, the aircraft, if the aircraft say this nozzle is choked and we obtain a speed equal to 600 meters per second, okay, which is the sonic speed at the choked condition. Okay, when sonic speed will obviously occur at choked condition, sonic speed at the nozzle exit, okay, 600 meters per second. But for the ambient condition, the speed of sound may be say 320 meters per second. Now if the aircraft flies at 450 meters per second, it can be driven forward, moved forward by the generated by the 600 meters per second exhaust gas that is exiting. But obviously still the aircraft is supersonic because it is flying at 450 meters per second, which is higher than the speed of sound in ambient air. That is why it is possible. Is it clear?
Yes, sir.
Okay. So we will discuss about little bit about diffuser and then we will end the class today. Okay. So and the other parts. So this compressor, combustion chamber, turbine, these things already are known to you right now. How to do the calculation. We will then see about the nozzles in the next class, convergent and convergent divergent nozzles in the next class. So if we know about the diffuser and nozzles, we are able to do all the calculations, right? Because the other parts already know how to tackle. Then we will solve a problem on that. Maybe after mixing, we'll see. So this diffuser, what is the role? The role is to increase the pressure, because otherwise there is lot of kinetic energy that is available, because the air is coming at a very large velocity relative to the engine. Okay. Actually, there is maybe a static condition, but the engine is flying forward at a high velocity. So relative to the engine, the air has a high velocity. So why waste that kinetic energy, right? So we can use that kinetic energy to increase the pressure. Okay. This effect is known as ramming effect. Okay. So by using this, the kinetic energy to increase the pressure, what is the advantage? We can decrease the number of stages of compressor. We can decrease the compression ratio in the compressor, because some of the compression occurs in the diffuser itself. Okay. So as a result, compressor work output can be, work input can be reduced. So turbine work output can be reduced. So you get more enthalpy for expansion in the nozzle. Okay. So diffusion is a very important process, and diffuser is a very important component of the of a jet engine. Okay, any jet engine. So what happens in this process? So ideally, so at the inlet, the temperature is say TA. Okay. So and the velocity is equal to VA. Okay. So what is the stagnation temperature at the inlet? Stagnation temperature we can calculate as, we will write obviously as T0A. T0A is equal to TA plus V square by 2CP. You know what is stagnation temperature, we have discussed, right, in a couple of classes back. So stagnation enthalpy H0 is equal to HA plus V square by 2. So T0 is equal to TA plus V square by 2CP. Okay. So if we could have, using first law, you can determine that if we could have reduced this velocity to 0. Okay, first let us consider that if we can convert the entire kinetic energy into enthalpy, the static enthalpy at the exit of the nozzle will be equal to H0A. Okay, and the stagnation enthalpy means basically the static enthalpy will be equal to the stagnation enthalpy, because velocity will be 0, and the temperature will be equal to T0A. Okay, but now if there are frictional losses, what happens in frictional losses? Frictional losses leads to, like, some energy gets converted to, say, some kinetic energy gets converted to thermal energy due to frictional losses. So ultimately, we are not losing out on the enthalpy. Even if there are frictional losses, ultimately the enthalpy that will be obtained at the exit of the diffuser is still equal to H0A, but the entropy will increase. Okay, so instead of H0A point, we will be at the same temperature point, but at H01 point, and temperature will be T01. Okay, so what will happen is that entropy increases, but the static temperature remains same as for the case of an ideal, like without friction. So in real case, the process goes from A towards the right hand side like this and ends at 01 point. Okay, I hope up to this point it is clear. Just let me know if it is not clear. Okay, so this is how we can find out what is T01. Okay, so what happens to the pressure? However, the pressure will decrease. Okay, because at 0A point, the constant pressure line is P0A, but at 01 point, the constant pressure line passing through this is P01. Okay, so and we can see that P01 is at a lower constant, means P01 will be actually lower than P0A. So the pressure is lower than what we would have obtained if there were no frictional losses. Okay, so because of frictional losses, we get slightly lower pressure in the diffuser. Okay, and that we will define today in a few minutes, couple of minutes, by using a diffuser efficiency. Okay, so now let us see the role of the diffuser. So we want to find out how much is the increase of temperature and pressure in the diffuser. Okay, based on inlet Mach number. If we know the inlet Mach number, say inlet Mach number is 0.8 or 1 or 2. Okay, what will be the increase in temperature? What will be the outlet condition? That is what we want to find. What will be T01 and P01? Okay, that is what we are interested in. So to do that, what we will do is we will try to calculate T01 by TA. Okay, assuming Cp and Cv is constant and gamma is constant. So T01 by TA, because T01 is equal to T0A, so T01 by TA is equal to T0A by TA. Now T0A by definition is equal to TA plus Va square by 2Cp. Okay. So I can write T0A by TA as 1 plus Va square by 2Cp TA, right? So what is Cp? Cp can be written in this form. Cp is equal to gamma R by gamma minus 1. How? Because Cp by Cv is equal to gamma by definition of gamma. So Cp by, what is Cv? Cv can be written as Cp minus R. Okay. So because Cp minus Cv is equal to R. So Cp by Cp minus R is gamma, and if you rearrange the terms, you will get Cp is equal to gamma R by gamma minus 1. So we can replace the Cp here by gamma R by gamma minus 1, and we will get a relation of T01 by TA is equal to 1 plus Va square by 2 gamma R by gamma minus 1 TA. So if you take the gamma minus 1 and 2 outside, okay, what we will obtain is T01 by TA is equal to 1 plus gamma minus 1 by 2 Va square by gamma R TA. Now what is gamma R TA? It is the speed of sound square of the speed of sound. Root over gamma R TA is the speed of sound at the ambient condition. So this is square of the speed of sound. Speed of sound is denoted by C. Okay, so it is CS square. So what is Va square by CS square? It is Mach number square. Okay, so ultimately we see that T01 by TA is equal to 1 plus gamma minus 1 by 2 Ma square. Okay, so if we know the Mach number and the ambient temperature, we can find out the exit temperature at the end of the diffuser. Okay, at the exit of the diffuser. So the next question is how to find the pressure. Because of pressure losses, the pressure is not equal to stagnation pressure. If there were no pressure losses, how I will take 5 minutes extra, okay, and we will finish. How would have we found the pressure if there were no pressure losses? What would have been the pressure at the exit? What will be the way to calculate the pressure at the exit if there were no pressure losses? Once we find T01, if T01 and T0A are unknown, based on Mach number, what will you do next to find the pressure?
We can use isentropic relation.
Yes, correct. It's very simple, right? We can use isentropic relation. So P0A by PA will be equal to T0A by TA to the power gamma by gamma minus 1. And T0 by A by TA is already 1 plus gamma minus 1 by 2 Ma square. So P0A by PA will be 1 plus gamma minus 1 by 2 Ma square whole to the power gamma by gamma minus 1. So we could have found this. But the main problem is that there is a pressure loss. So to account for that pressure loss, what we do is we use efficiency. Okay, so we can define this efficiency of the diffuser in two ways. Both have the same meaning. Both account for the frictional loss, but it is how they are expressed. They are expressed in different ways. So one efficiency is known as ram efficiency of the diffuser. Okay, so this ram efficiency is defined as the actual rise in pressure P01 by PA, P01 minus PA, sorry, divided by the ideal rise in pressure P0A minus PA. Okay, so if we give the RAM, if we know the RAM efficiency, say RAM efficiency is 95%. So then how will you find P01? I will take 5 minutes extra. We will finish. Wow, this topic is left. If the RAM efficiency is known as 95%, so then how will we find P01? First, we will calculate P0A using the isentropic relation, right? So P0A by PA, as I have just explained, is equal to T0A by TA to the power gamma by gamma minus 1. So once you obtain P0A, we can calculate based on eta rem, because P0A will be known, PA will be known. Only unknown will be P01. We can calculate P01 from here. Okay. There is another efficiency that can be used to describe the efficiency of or the losses in the diffuser. This efficiency is known as isentropic efficiency, but it is described in a slightly different way as compared to the isentropic efficiency of the compressor. Okay, so here it is the efficiency. So if we extend the constant pressure line and it curves the isentropic line at a point 0,1s. Okay, this constant pressure line, actual constant pressure line P01, it curves the isentropic line at 0,1s. So we can define this isentropic efficiency as the rise in temperature or rise in enthalpy that occurs in that case. So H01s minus HA by the actual rise in enthalpy that is occurring, H01 minus HA. Okay. So this is also equal to T01s minus TA by T01 minus TA. Is it clear how it is defined? So it is defined artificially, in an artificial way, as if the constant pressure line is extended and curves the isentropic process here at a point, and if we call this point as 0,1s, then the definition of isentropic efficiency is H01s minus HA by H01 by minus HA. So basically it is equal to the length of this line by the length of this line. Okay, so this by this. Okay, so T01s minus TA by T01 minus TA, because T0A is equal to T01. This is also equal to T0A minus TA. Okay, so we can. So how will we find? So ultimately now we have to find the pressure. We know already how to find the temperature. So if RAM efficiency is given, we can easily find the pressure. But if isentropic efficiency is given, how will we find the pressure? Let us see quickly. So if isentropic efficiency is given, so this is equal to T01s divided by TA minus 1. If we divide both the numerator and denominator by TA, T01s by TA minus 1 by T01 by TA minus 1. If you take this to the left hand side, you get eta d into T01 by TA minus 1 equal to T01s by TA minus 1. What is T01 by TA? We have already obtained today. T01 by TA is 1 plus gamma minus 1 by 2 ma square. So this is equal to 1 plus gamma minus 1 by 2 ma square, and this extra minus 1 is there. So minus 1 and 1 gets cancelled. So we have here gamma minus 1 by 2 ma square into eta d on the left hand side. What about T01s by TA? What is T01s by TA? From the diagram we can see that T01s by TA using the isentropic relation, it is equal to P01 by PA to the power gamma by gamma minus 1. Sorry, gamma minus 1 by gamma. So P01 by PA to the power gamma minus 1 by gamma minus 1. Okay. So now we have related, we have obtained a relation where we use the value P01. So now if you rearrange the terms, P01 by PA to the power gamma minus 1 by gamma is equal to 1 plus eta d gamma minus 1 by 2 ma square this side. Okay, so you've just taken the 1 to the other side, and then you take out this to the other side. So P01 by PA is equal to 1 plus eta d gamma minus 1 by 2 ma square, the entire thing to the power gamma by gamma minus 1. So this is how. So here everything is known. So if diffuser efficiency is given, Mach number is known, gamma is already known, gamma for the air, PA is the ambient pressure, so we can find out P01. Okay, and the final point to remember here is that eta d and eta rem are related. Okay, so they are related. So if one is known, obviously we can calculate the other. Okay, so they are related by this basically because we know that P0A by PA is P0A by TA to the power gamma by gamma minus 1. So it is the same information in different form. It is the same information. What is that information? Information about the losses, but in different form. Okay. So I will leave you with this exercise to do. It is there in the notes. I have already uploaded the notes. So TA is equal to just to because this part every year the students find it difficult, okay, to understand this process, diffuser process. It is somewhat different as compared to the compressor. So if you try to do this exercise, then you will understand this better. You will get to know if there is any confusion, and you can clarify the doubt in the next class. So TA is equal to 223 Kelvin, the inlet temperature, and inlet pressure is given as 0.2 bar, and the exit pressure is also given. Somehow we have found that to be 0.3 bar. We have measured it using a probe that it is 0.3 bar, and the Mach number at the inlet is 0.8. We need to find out what is the isentropic efficiency of the diffuser, eta d, and the RAM efficiency of the diffuser. Okay, try to do this problem, and if there is any confusion, let me know in the next class, and we will discuss. Okay, very simple. It will not take much time to do, but it will clarify here if there is any confusion. Okay, we will stop this, and the syllabus also is up to this point for the exam. Okay, so this part is also included, whatever small things we have discussed. So I can ask you simple things about turbojet, whatever, like to draw the turbojet cycle, or means I have already said the question long time back, but I may have included this, or may not have included this, assuming that I will be teaching this. So up to the what we have discussed in today's class is the syllabus for the exam. Okay, so any questions? Friday class will still be there. Thursday there is no class. Okay. Friday whatever we discuss is not included in the syllabus. So you can study up to if you study up to this point, it should be sufficient for the exam. Any questions?
Sir, in this case, is it appropriate to consider isentropic efficiency? Why? Because in this enthalpy is increasing, right?
Actually, it's a very good question. So we'll not stop the recording because it may be useful to students later on. So it is not because of, it is good question in the sense that it is not because of enthalpy is increasing, we cannot define isentropic efficiency, because for the compressor also we can define isentropic efficiency, right? And
But
in the
for
compressor,
we are giving work, right?
very good point. Very good point. Correct. So in the compressor, we are giving some work to increase the efficiency, right? Cannot I erase? So that's why the compressor efficiency makes sense, that the actual work input we need to provide is larger than the ideal work input. In this case, there is nothing like that, right? The enthalpy that is increasing is same in both the cases. So that is why I was saying a few minutes back when I was defining the isentropic efficiency, that artificially we are creating a point 0, 1s. Okay, so it is an artificial point. It does not have a physical meaning. It is just defined so that we can relate it to the decrease in pressure. Okay, because there is no decrease in temperature, there is no decrease in enthalpy. So whatever enthalpy we are obtaining, stagnation enthalpy remains same, static enthalpy is increasing, and whether there is friction, how much is the friction, it does not matter. The static enthalpy we will obtain will be same, because frictional losses also manifest as enthalpy, right? So the frictional losses also will lead to increase in enthalpy. So it's a very good question. So physically, it does not make any sense to define an isentropic efficiency. Artificially, we define this efficiency just to define a parameter so that the pressure can be, so it can be related to the losses in pressure. Okay. So ideally, it makes more sense to use the RAM efficiency. Okay. Ideally, it makes more sense to use the RAM efficiency to define the pressure losses. But this is another way of defining the pressure losses. Okay, because what is happening is that we can measure the pressure at the exit of the diffuser using probes, and then you can calculate what will be the efficiency of the diffuser based on that pressure. Okay, if you measure, because we can calculate measure the pressure, so you can define efficiency based on that pressure artificially, and that efficiency is known as isentropic efficiency. But it's a very good point that it is not similar to the efficiency of a compressor or a turbine. Okay, it is artificially created just for accounting for the change in pressure. Okay, is it clear?
Yes, sir.
Yes. So this is actually that I would have asked you, but you have asked. So it's a very good question. Any other question?